Okay, thank you, Norbert. Okay, I'm going to talk about the Gaussian mixture models and the incomplete tensor decomposition. Is my voice okay?
Yes, I think so.
Sounds
okay.
fine.
If you need louder or lower, let me know. Okay. Anyway, so what is Gaussian mixture random variable? It's actually it's like this. So that means it's I'm sorry, it's because I cannot see the top of it. Okay, a random variable y is so the mixed model actually is is a mixture of several random variables. Let's say suppose the total number is r. So and the y equals one of the random variable is with probability the same omega I. So in other words, okay, y operates this distribution with omega 1 and then this one with omega r. Okay, and of course the weight is positive and summation equals 1. So the density function. So the density function is like this, is the summation of this. So the density function is simple. Okay. Now, what is the task of learning Gaussian mixture model? So that is from the observations of y. So we need to estimate the parameters, the mean variables, and the covariance matrix for each individual one. So we need a sampling. We need a sampling of y. Well, if r equals 1, then the problem is easy. So you just take the average and take the covariance matrix, and we can estimate them quite well. But however, if r is bigger than 1, so if we just do that, then then you can, as you can see, then it's not convenient to recover them. Actually, well, there exists a large amount of work on this, and the application is enormous. So in the speech recognition, signals, there's a lot. So the classical, there is a lot of work on this. So the classical work is, one of them is about the expectation maximization or the EM algorithm. So the motivation for this actually is quite simple. So that means from the observations, we can estimate the probability and we maximize it, and then maximize and get the mean vector, the mean vector and covariance. And also there is a lot of methods. For example, that means the observation vectors y maybe usually is one higher dimensional one. People we can project in lower dimensional space and then do it. Or there is another class of work is a moment based. So that means is based on the moments of the observations, and then we do apply tensor decomposition. Actually, this four authors actually has done a wonderful work on this topic. So actually, my talk today actually is also follow the moment approach. It is still based on tensor decomposition, but however, is incomplete. Why do we use the word incomplete? Actually, there is a reason for that. Well, I'd like to mention that for this work, they usually they consider the focus on the case of filial covariance. So this means the covariance matrix is the multiple of the identity matrix. So in this talk, I consider the more general case, the omega is each sigma I is diagonal, so it's not a multiple of identity. So how should I do this? So that means okay. So from the moments actually divide, we have first order, second order, and third order. First order is easy, just is it's a convex half. It's a convex combination of the mean vector. The second order matrix is also relatively easy, and you just expand it because we know the distribution of y. So you just expand it and we get this. Okay. And third order moment, we can do something similar. Okay, you just expand it and then we get the omega I of the cubic power of the mean vectors and plus the remaining terms. Well, I would say the remaining terms is not fun. If you expand it, theoretically there is a formula, but how it's quite complicated. And actually it's So now here, I mean, in this talk, I assume that sigma I is diagonal. Okay, is a diagonal. If it's diagonal, then well, we can get a nice formula for the third for the cubic power. I mean, for the third order moment. So we just expanded. Okay, the first one we like the first term. So is is the summation of the cubic the tensor powers of the mean vectors. And here we also have this, and we have Aij actually is, but Ej, here Ej means the J is unit vector. So it means the J's entry of Ej is 1 and all the others are zeros. Okay, now what is an incomplete tensor moment tensor? So that means, when sigma I is diagonal, we have this formula for the third order moment. And then actually, as you can see, we like the first item. Okay, we don't like the others. The others way is because it is Aj, the formula for Aj is already complicated. And we consider this formula, but how you see from this formula, then you can see that if the labels I1, I2, I3 are distinct from each other, then these two tensors F and M3, they are equal. So this is the observation. Okay, they are equal. And then, so we consider these labels, so that means the labels, all the I1, I2, 3, they are distinct from each other. So now here we can see that the subtensor, F, okay, the subtensor of, when we consider this label set, the subtensor of F then is the same as the subtensor of M3, okay? So this is the observation. Now, okay, now the question is, okay, for this label set, these two subtensors are the same. Now the motivation is, okay, because the reason why do we consider this subtensor, the F is, the entire tensor F is not available. But this subtensor is available because it's equal to the subtensor of M3. But however, M3 can be estimated from the sampling, okay? So this is the idea. Now, the computation task is for the given subtensor, we look for the incomplete tensor decomposition. So that means we want to find vectors V1 to VR so that they are the match for this subtensor. For the labels in the set omega. Outside the omega it doesn't matter. So we because of, the purpose we want the vectors V1 to VR. Okay. Well, you can think about what looks like this is the tensor completion problem. Looks like, the subtensor is available, so we want to complete the missing entries of the tensor, and then we do tensor decomposition. So this is a very straightforward approach. But however, in this work, so, tensor decomposition is discouraged. So it's not encouraged, discouraged. So what are reasons? The reason is actually this. For tensor completion, well, actually the theory is very premature. So it looks like for the most of our kind of work is a kind of convex relaxations. For example, minimize the nuclear norm or minimize the trace of the flattening matrix or whatever, something like that. Okay, and then I'd like to mention that to compute the nuclear norm, actually the problem is already very difficult. The problem itself is hard. And to compute the trace minimization of the flattening matrix or something like that is, that one is relatively easy, but it's still quite expensive because we want to flatten the tensor into a big matrix, and then we solve the semi-definite problem, and that is not fun. Yes, it is very computationally expensive. Okay, and more seriously, even if we do this, the complete tensor is not low-bound. Okay, people might think I do the trace minimization, run nuclear norm minimization, we might get, actually the answer is not the truth. So that means, if we do this, the fact is we spend a large amount of computation expense. However, we did not get what we want. So actually, the numeric experiment demonstrates this one does not work very well. Okay. So that's why we should consider also. So we compute the tensor decomposition from the subtensor directly. So here is what I propose in this talk. So it's okay. So from the subtensor, we compute this decomposition. But of course, the match for the labels in the set omega, and the method is based on actually my earlier work on the generating polynomials. So it's So what is the what is the idea of this this work? Actually is very simple. So we consider this tensor decomposition. So you might ask, what are, okay, we want to determine the vectors V1 to VR from the tensor. So what are they? What are these vectors? Actually, these vectors are the common zeros of some polynomials, of some polynomial equations. So we want to, if we can get those polynomials, then we can determine these decomposing vectors. I mean, for the subtensor the idea is similar. So we can still use these polynomials to estimate these vectors. But however, since the tensor is not completely given, actually, we cannot do for all the cases. Actually, we still have there's still some restrictions. So I mean, in this paper, we have these assumptions. So the vectors mu1 to mu k are linearly independent. So I'm sorry, the k should be r. Okay, I'm sorry, it's not r. It's not k r. Okay. And R should be less than 1/2 of the dimension. So D is the dimension of the vector Y. Okay. So it's about 1/2 of the dimension. But however, the tensor is not completely given. Okay. Only for this subtensor. So it's I would like to mention that actually these two assumptions are sufficient, but not necessary. I mean, even if these two assumptions well, if the second one actually is important, if second one is violated, then it's hard. First one, I mean, if the linear dependent or nearly linearly dependent, actually it may still work, but however well, there is some issues there. But anyway, these two are sufficient conditions. Okay, to introduce the method, so let me introduce some notation. So first we can go n equals d minus 1. So dimension minus 1. Okay, that is n, and we labels the tensor. So tensor, the labels start from 0. So that's why we n equals d minus 1. Okay, and then we define this bilinear function. So you can see that every tensor can be viewed as a multilinear function. Yeah? So if we do this now, so here P is a polynomial. So if the P is a polynomial like this, then you apply this bilinear function. That means you just replace this monomial by the tensor entry, and you get this. Okay. So what are the generating polynomials? Actually, here is a definition. So let's say polynomial T of degrees 3. Actually, well, I mean, for the most interesting case, T should be the degree is less than 3. That's better actually. I mean, we apply this bilinear function. So if the product is 0 for all the degrees, that is no bigger than 3. So the reason is that if the degree is bigger than 3, then this one is not defined. Okay. So that means now how do I do this? So that means we consider this set. So I mean, for example, we consider set R. Here I assume R is given. Okay. So that means we consider this set B0, so that is x1 through xr, and then you multiply it with xr plus 1 and xn, and then you delete the ones in B0, and then you get this. And then for each, this one is each one of them is a quadratic term. It's xi times x here. And for this quadratic term, then we do this. Consider polynomials of this set. So the first r terms are the linear terms, okay? And the last one is a quadratic term. So that means this polynomial has degree 2, and then to apply this definition, actually we get is the n+1 equations. Okay, n+1 equations. And then actually, the coefficient of this matrix is represented by a matrix G. So if these equations are satisfied, we give the name. So G is called a generating matrix. Okay. So so because F is, here the issue is that if F is the subtensor for F is given, all these entries are given. You can see I, J, T, 0, K, T, So if all these three are different, then the coefficient of these equations can be determined. Okay. Okay. Now let's see what is the relationship actually is that. So we consider for the given G. So we consider these polynomials actually well. So we have this conclusion. So that is suppose. Here we assume suppose the tensor have this decomposition. Here the trick is we scale the first entry to be 1. We scale the first entry to be 1. So that means we have U1, UR, so the vectors in the n-dimensional vectors. So here is the conclusion. So that means here we need to make some assumptions. If the subvectors I mean, the subvectors one. I mean, 1 through R. So that means subvector U1. I mean, the first entries of U1 through UR. The are linearly independent. Then actually we can show that there is a unique matrix G satisfying this. So matrix G is unique. So that is very good. So I would say if you the vector scale, that means here actually the assumption is stronger than what I mentioned earlier. So I assume these subvectors are linearly independent. Actually, this one is, I mean, if U1 through UR they are linearly independent, then they always exist a subvector of this length R that is linearly independent. So we can, I mean, for convenience, I just assume the first R ones are linearly independent. Okay. So this is for the existence of G. So from the tensor decomposition. Okay. Now, how do we use the GP to get the tensor decomposition? Actually, here is the conclusion. So suppose, I mean, this one is the G is the generative matrix. Then we satisfy this equation. Okay. Actually, we can show that each decomposing vector satisfying these equations. So this is linear. I mean, it's kind of eigenvalue equations. So you can see the first vector UX1 to XR is the eigenvector, and XL is the eigenvalue. So here L is from R plus 1 through N. Okay. So actually, from here we can see that actually this is a set of eigenvalue equations. So here is an example. Suppose here we consider this rank 2 tensor. So in the rank 2 tensor, R equals 2, the B0 equals X1, X2, and B1, I mean, the remaining set. I mean, you use that. Actually, we get N3, N4, N5. We get these 3 matrices. Actually, I mean, these 3 matrices, actually, they are simultaneous diagonizable. Okay, that's simultaneous diagonizable. Actually, from that, and from the eigenvalues, eigenvectors, we can recover these 2 vectors. Okay. Okay, now what is the algorithm? So algorithm actually is, I mean, we just do that. Okay, so the input is the subtensor, and we assume the rank is this small. Okay, so it's so we did first of it. I mean, what's the idea? So that means we determine the matrix G. Okay, I mean, from solving a set of linear equations, and after G, then we formulate this matrix. And here we apply a genetic linear combination. So why do I apply a genetic linear combination? Because that means, I mean, so if the tensor has rank R, then this matrix are simultaneously diagonizable. But however, if we don't want to diagonalize it individually, because there is a numerical issue, and also if there is a repeated eigenvalue, then there is a trouble. So here we apply genetic linear combination, then it makes better. Okay, and then we consider unit length eigenvectors of this combination of this matrix, and then we apply this quadratic product, and we get that. And then after we get that, then we consider UI and VI to this. Actually, we need to still need to determine the scalars gamma and lambda. So here, this question is easy. So why? Because there is a pattern, so we can solve it. I mean, we don't need to solve nonlinear equation. We only solve linear least square. So these scalars can be determined by using linear least squares. Okay, and after we get them, we get the tensor decomposition formula. Okay. But however, as you can see, because the tensor actually, the subtensor actually is not exactly available. We can estimate it. But estimate, of course, for example, if somebody always have a mistake. Actually, here is. But however, the good news is we can still apply this method. Now, what do I do? I mean, if the tensor has a noise, actually, we can do. I mean, what we can do very simple. I mean, we can solve linear. I mean, we don't solve linear equations exactly. We replace it by linear least squares, and we can still do it. Here is the conclusion. So I mean, under some technical assumptions, so if the subtensor is sufficiently close to a low rank one, I mean, the rank R. Okay, here VSM R is given. So if sufficient close, then this one will produce a quasi-optimal tensor decomposition. I would say this one is related to the condition number. I mean, as introduced by Nick and Paul. but however, the condition number can be very large. But however, here we consider the tensor is given, so that means it's locally actually is numerical. But however, the relation of them is the ratio that depends on the error. The ratio of the error depends on the condition number. But however, the good thing is we only need to solve linear least squares and eigenvalue decompositions. Okay. Well, now the issue is what do we get the rank R? Usually R, if R is given, that's perfect. If R is not given, then usually, that's going to be very difficult. But however, if R is small, then there is a practical way to estimate it. So what is that? The story is very simple actually. We consider the flattening matrix. Okay. For cubic order tensor with flattened matrix, actually, here is a very basic fact. If R is smaller than D, then these two ranks are the same. If R is bigger, that is very complicated. But if R is smaller, then these two, under some geometric assumptions, they are equal. So that means we can use this flattening matrix to estimate the rank of R, of the rank of the tensor. Okay. But however, as you can see, because the tensor is not fully available, we have some of them are known, some of them are not. How do I do actually? Well, the life is not that bad actually. But if R is less than 1/2 of the dimension, then actually we can consider this submatrix, for example, for this matrix, and for this submatrix, and for this matrix, actually, under some generalist assumptions, the rank of these two submatrices will equal to the rank of F. But of course, here we assume the rank is less than about 1/2 of the dimension. If R is bigger than, I don't know, it can be, the question can be very difficult. Okay, so this is the estimation of rank R. Well, now let's discuss how to estimate the parameters in the Gaussian mixture model. So here is the same, because it means the y. We have several normal random variables. So here is the issue here. As I mentioned here, we need to assume R is less than or equal to 1/2 of the dimension, and we have this. So that means first of all, well, I'd like to say that actually, yeah, here is the issue. So for the tensor decomposition, actually, well, let me say, for tensor decomposition, there is a scaling issue. This one, what we want is the summation of omega-1 to be positive and equals 1, right? But however, for tensor decomposition, there is a scaling issue. There is a unitary, unitary scaling, scaling issue, and we should be able to do. So that's why we need first order moment. Okay, now here is what, well, here we don't need the second order moment. We only need the first order and third order. So that means we do this, and then, so how should I do? So suppose here is a tensor decomposition. Here we assume actually, if there is in numerical combinations, we always assume that approximate equal, okay? That approximate equal, then we do this, then we scale it. Now, how do we scale? Then we do this way. Because we need to use, we also need to use the first order moment, and then we apply this, then we estimate this way. And after this, then we can prove, actually, if everything is an equality here, then this bottom two are also equality. And we can do this, okay? And of course, there might be,
You lost your sound. I think he accidentally muted himself.
Okay, so here is,
you're back.
Is there a question?
No, I said your sound is back, and you have 5 minutes left.
Okay, very good, thank you. Okay, now after we get the weight and the covariance matrix, how do we get the covariance matrix? Here is the story. So that means we take the subtraction. Then subtraction, we have the remaining tensor has this form, okay? The remaining tensor has this form. And then actually, Aij, we can express Aij in this format. But here is the thing is omega I is available now, the mu I is available now, but we sigma ij squared, we don't know. So how can we do? Well, sigma ij actually, well, first, we can get the vector Aj from this pattern. Okay, from this pattern, we can get this. So the vector Aj is available. Now, how do we get the sigma ij squared? Well, simple, we solve linear least squares because omega I, mu I is available, Aj is available. We just solve linear least square and we get it. Well, Some people might wonder, how about if this number is negative? I mean, here is a story. If the moment represents the distribution of the GM module, then this should be supposed to be positive. But if it's negative, what we can do? We can force it to 0 or to choose, a positive number. So we can handle that, but we can do it numerically. Okay. So, so here is the robustness. As I mentioned, we apply sampling. Sampling, is never exact. So we can do approximations, and that's supposed to be close. Okay, but how close are they? That's the statistical issue. We don't know. Anyway, so here is the conclusion. So that means if the conclusion under these assumptions, so that means is if the distance is if the errors of this estimation is small enough, then we have these conclusions. That means computed weight, computed mean vector, and computed covariance should be sufficiently close to the original one. Okay, so here is the conclusion. So that means this is robust. Okay. Okay, here I give some report some numerical experiments. So it's about here the random tensor like this. First we generate random ones. Okay, random ones we do it, and here this is here I only report the relative error. Okay, the absolute value actually is very small. The relative error is like this. It's looks like is smaller than 1. It's close to. In the level of 0.9. It's between the 0.9 and 1. Actually, this one is. I would say that small r is the better. If r is small, then is because r is small, then that matrix actually is widely. Is 4-column rank. It's actually that is one. For the diagonal Gaussian mixed model, we can do also something we make about these samplings, about samplings. But here we assume sigma is diagonal. If sigma is not diagonal, then I don't know. Maybe assumption we assume that maybe the sequence of sigma I to be simultaneously diagonalized, but that is maybe one assumption. But however, for general case, we don't know how to do that because it's quite complicated. And for this, and we have this table, so that means it's here is the ratio, okay, and here we compare with the expectation moment method, and okay, and so also that means we apply the method, so it's to do some picture classification. Actually, here is this. We have 8 pictures, for each one. Actually, each one of them is a Gaussian mixture model. And then we compute it and then do it. And then after that, we get a new mix. And suppose we give a new message, a new picture, then we do the same estimate and choose the correct one. Actually, that is, but so that is, here is a ratio. The way we compare with the EM method. Okay, so it's, unfortunately for the first 2, our performance is lower, but for the others actually is better. It looks like the benefit is large. The first 2, I don't know why, what is the reason, but maybe one reason is the first 2, they are very close. Relative looks like close, maybe the reason. But I don't know the true reason. Okay, I guess maybe that looks similar. Maybe just I don't know. Anyway, looks like for others, looks like it can tell better. Anyway, so let me conclude the talk. Actually, here I discussed the Gaussian mixture model with diagonal covariance matrix. If the covariance matrix is not diagonal item, it's a future work. Actually, it's very difficult. And then the problem is reduced to an incomplete tensor decomposition. And then I use generating polynomials to compute the decomposition. Again, there is some robustness proof of this. The conclusion actually is simple. If the subtensor is accurate enough, then the output should be also, it's kind of quasi-optimal. Okay, and give some numerical experiments. Anyway, thank you very much.